Move into looking at our VSEPR theory and how we use this to predict the shape of a molecule. But what if the molecule isn't just teeny tiny and there's only one center atom like this? What if you've got a molecule that looks like this? Then essentially what this is saying is you're going to have to figure out what the shape of the molecule is around this atom that's going to be the center to this one, and then what's the shape around this one, and then this one and this one. So because molecules aren't just neat and tidy and very small, we could be looking at huge macromolecules. I could say there's a tetrahedral shape around this center atom, but it might be different for the second one. Now, this just so happens that it is tetrahedral around all of them because there are 4 bonds around each of these center bonds. And each bond is a bonded pair of electrons and not a lone pair of electrons. So that changes, doesn't it, if it's going to be a lone pair of electrons. So that's just to get us going. I already filled in part of this note, so it shouldn't take us too long. But the first example on this page right here are for ones where you can identify the center atom. Just have a look at the examples that you've got. Clearly, carbon tetrachloride. Carbon is the center atom, and you know that. You do you can do a Lewis dot structure. We've already done that. You can draw a line diagram. Here we go. Now let's move on to figuring out what the shape of that molecule is going to be. This one's fairly easy as well, right? Ammonia. You can see there that the nitrogen is clearly going to be my center atom. Water, oxygen's in the center, sulfur is in the center, and carbon is in the center. Okay, so now you can see though that those center atoms have differing amounts of bonded pairs of electrons. So for example, carbon tetrachloride. How many electron pairs are there around the center atom or the central atom? This is key. Highlight that. We're looking at the center atom. I don't care how many pairs of electrons are around each of the chlorines because that has no factor into the shape of the molecule. All I'm concerned with are how many are around this center atom right here. Okay, so picture this is carbon, which it is. Picture these hydrogens, pretend that they're chlorines. You can see here that around my center atom, I have 1, 2, 3, 4 electron pairs. How many are bonded and how many are lone pairs of electrons? 1, 2, 3, 4. They are all bonded. There are 0 lone pairs of electrons. Okay, so I'm going to start, and I know that this is a tetrahedral shape. I have 4 things around the center atom, and each thing around the center atom is a bonded pair of electrons. That makes it easy. Now, what happens if I move to the next one, where around nitrogen, I have 4 things that are around it. Let's change my highlight here. 1, 2, 3, and 4. 4 electron pairs. How many are bonded and how many are lone? And I even have one of these right here. You can't see the lone pair of electrons, but they would be here in a big cloud. 3 are bonded. 1 are lone. How do I draw that? Okay, I take my tetrahedral structure, that's my base starting point, and I change it from having 4 electron pairs around it that are all bonded, and I knock off 1, and I come up with the shape that shows me that there's a lone pair of electrons here, which also has a negative cloud, right? It's got a negative charge to it. And the interesting thing about this cloud is that it actually pushes down these other bonded pairs just a little teeny bit, okay? So instead of having just the 4 things around it, I start with my tetrahedral shape. I take off 1 bonded pair, and I'm left with 3 bonded pair, 1 electron pair that's lone, and I'm going to put a little cloud like that, like a little Mickey Mouse ear around it, and it has a different name. Okay, this is called a pyramidal shape. Do you need to memorize all of these? No, we used to do that, but now look, you can take your PhET simulation, and I can go back and say I want to start with 4 things. Oh, let me add one. Okay, 4. That's my tetrahedral shape. Let's just move it so you can see it maybe a bit better. How about there? Okay. I want you to see what happens to the bond angle when I take away one of those bonded pairs of electrons and account for it as a lone pair. Watch this. Okay, what happens to the angle? Can you see that? It's still showing as 109.5, and every time I add more bonds to it that are bonded pairs of electrons, it will change the shape a little bit, okay? Now, this probably wasn't the best example to use then for this one, because the angle that we're going to end up using is generally about 107 degrees, because it sneaks these down just a little bit because the lone pair of electron takes up more space, okay? So the angle that I want you to add in from here is that instead of 109.5, it now moves it down to 107.5 degrees, simply because the lone pair of electrons takes up more space, it sneaks these down, and they get pushed a little closer together. Okay, let's see what happens now if I still have my starting point as my tetrahedral, because I'm going to count around that center atom of oxygen for this one right here, that I have 1, 2, 3, 4 pairs of electrons around my center atom. Okay, how many of those are lone and how many of those are bonded? 2 are bonded and 2 are lone. On your diagram, you're going to start with your tetrahedral shape. You're going to take off 2 of the bonded pairs, and you're left with your molecule where the lone pairs of electrons are here and here. Okay, and again, if you take off any 2, you're going to end up with the exact same shape. Give it a try. Okay, I'm going to show them on my diagram here and here. That's the best way I can do it. They take up a little more space. The angle sneaks down a little teeny bit. And now the angle between here and here is the same as my water molecule, which is a bent shape. It's also called a V-shaped. Sometimes it's called angular. It's all the same, okay? The angle, 104.5 degrees. Let me see if that one works over here, okay? If I have 4, an extra pair of lone electrons, let me get rid of one of those, and oh, it's still showing me a little bit more. If you go to the real molecule, oh, and water happens to be right up. Let's click on the bond angles. And this one shows it most accurately. I guess the other version doesn't show it with the actual molecule. So there you go. There's our water molecule. It's a bent shape, but notice the fact that the lone pairs of electrons take up a bit more space. They push the bonded electron pairs down a little bit, and the characteristic angle for water, this is one to memorize, is 104.5. Okay, on the bottom left-hand part of this PhET simulation, I can click on this one to show me what the actual molecular geometry is. It's bent, angular, V-shaped, same. If I click on this one, it shows me what my starting point would have been. So again, tetrahedral, you start with 4 pairs of electrons around it, okay? If I have all 4, it's tetrahedral, it's 109.5. If I have 4 pairs of electrons, but 3 are bonded and 1 are lone, it sneaks it down a little bit to about 107, 107.5. If I have 4 pairs of electrons around it, but 2 are bonded and 2 are lone, you end up with an angular shaped molecule, and the angle between here and here is 104.5. Okay, that's how it works with molecule shapes. And this is going to be important because, again, it tells us a little bit more about the polarity of the molecule once we know the shape. Okay, can you do the next one? Sulfur is going to be in the center. I have 1, 2, 3, 4 things around it, 2 and 2. Sulfur also, therefore, has 2 lone pairs of electrons, angle 104.5. See how those numbers are actually fairly easy to memorize? 109.5, 107.5, 104.5, just a little teeny bit less. Okay, next one, we've got CH3Cl. I have 4 things around carbon. I have 4 bonded pairs. I have 0 lone pairs. You can draw your lone pairs of electrons around chlorine. It's always a good idea to do that. And then, of course, we're back to our tetrahedral shape which is 109.5 degrees. Okay, fun, isn't it? Yeah, this is the VSEPR theory for shapes of molecules. Here's your explanation again for how to repel. Could you explain that on your own or talk to a friend and see if they can explain it? That's the best way to see if you understand it. All right, part 2, which is the last part here. What if you can't figure out what the center atom is? What if you have a molecule like ethene? Is this on our example? Ethene, right there, the second one down. Okay, if you had ethane, let me just show you the difference between these ones here. Ethane, you need to talk about the shape around this side and the shape around this side, okay? The next one on the list is ethene, and it's got a different shape. You still have to talk about the shape around here and the shape around here. But what if you have a double bond between the two? Okay, here's the rule. Double bonds are going to count as one pair of electron around it. So then I can see, if I hold it up, 1, 2, 3 things around here. What's the shape around this one with 3 things? It's going to be trigonal planar. What's the shape around this one? 1, 2, 3 things. It's trigonal planar. So you've got trigonal planar over here, trigonal planar over here, and look at that molecule. It's on the same plane. Okay, so here we go. That's the rule right there. A multiple bond, whether it's a double or triple bond, is only going to count as one. So all you need to do is show on your diagram which carbon you're talking about. I'm going to randomly say that's carbon 1, and that is carbon number 2. It's the same around each. Each carbon has 4 bonded pairs of electrons, 0 lone pairs of electron. What's that stable molecule shape? Something with 4 is a tetrahedral. Okay, how do you draw this? You could build it, you can draw it. I'm going to show you it's going to look like this, and the only thing I'm going to tweak, and if you've got a molecule kit or you've built it with marshmallows, here's what you're going to do. You're going to not take it all at the same plane for these guys. I'm going to tilt them on an angle. Can you see that? Now, why would I have done it a staggered way? It's staggered simply because, remember, here's a negative region, here's a negative region. If they're side by side lined up, they're too close together, okay? Maximum stability, minimum repulsion, and your molecule will look like this. So in bio class, when you have to build a huge molecule, when you're building a huge hydrocarbon chain, it's tetrahedral around each of them, but start with one, stagger it, start with the next one, stagger it, start with the next one, stagger it, and you can make them, right? Like you can see how it'll go up, down, up, down, up, down, like a little lipid molecule there. You've got a little tail, okay? All right, so think about that when you get to that in biology class as well. Okay, so when you draw that though, here's what I do. I start with my carbons in the center, carbon, carbon, and then I remember I had one on the same plane and another one on the same plane, flat, 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 and then of course they were opposite. So this one was coming towards me as this one was going away, and then this one's going away as this one's coming towards, just as best you can. But what do you remember? Add in a bond angle of 109.5 degrees, and of course that's tetrahedral for both of them. Okay, do you want to do one more, or do you think you've got this? Do you want to just fill them in from the sheet? Why don't I just show you the first one, and then you can go ahead and do the next one where the carbons are going to be a little different. Let's call this carbon 1 and this carbon 2. They're both the same. There are 1, 2, 3 regions around one carbon, 3 regions around the other that are bonded, because double bonds count as 1. 0 lone pairs. What's my name of the shape of this one? Look back if you need to. Trigonal planar. This is the one I've got built right here. And if you actually build it with that double bond in between, they are all on the same plane. So how do you draw that? Start with your double bonded carbons. Hydrogen, 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 and bond angle of 120 degrees. Okay? I'm going to let you do the next one. You'll see that there can be 2 different shapes on either side, and that is totally fine. So double check with that one. Make sure you know how to do that. And then I'm going to leave you to work through this last note using the solution set as you can, because, again, we're looking at a molecule where One side of the molecule could be polar or non-polar. And of course, it's this shape of the molecule that's going to affect the overall polarity. Okay, so that's it. Polar molecules, non-polar, and determining overall molecule polarity. I think I will let you work away at this, and then maybe we'll do a little tutorial where I can build some of the shapes and show you again. But again, see if this makes sense to you. Adding in the actual shape of the molecule now that we know how to apply VSEPR theory, and then you're going to look at that accurately shaped molecule to see which side of the molecule, if any, has some overall polarity. Okay, so it's linking in bond polarities, factoring in any lone pair of electron around that center atom, and then recognizing the fact that, yeah, there's going to be a slightly negative side and a slightly positive side. And then, of course, talking about all of the physical and chemical properties that go along with that. Okay, good luck with that, everybody. Let me know how it goes, and I hope you enjoyed learning about VSEPR theory.